So today I would like to review briefly some observational research that my group has been doing on the galactic correlates of supermassive black hole growth over most of cosmic time. And I will also talk about the application of this correlates work to model the growth of the supermassive black hole population via both accretion and mergers. A team of us have been working on these studies over the years, although I'd like to highlight in particular the huge efforts made in recent years by some of my group's students, shown in this top row at Penn State, as well as some of my group's postdoctoral researchers, shown in this bottom row. All of this work has grown out of the X-ray and multi-wavelength surveys work that my group has been doing for many years, which forms key groundwork. And the X-ray survey community generally has had a good run over the past 25 years. We've had many good successes. We have now clarified the contribution of active galactic nuclei, or AGNs, to the cosmic backgrounds of the universe. The X-ray surveys have revealed most, or at least much, of obscured supermassive black hole growth in the universe. We have revised our understanding of AGN evolution and the cosmic balance of power. That is, since the formation of galaxies, how much power has been made by supermassive black holes compared to stars. We have also achieved a much better understanding of high redshift AGNs and their contributions to reionization of the universe. And we have advanced understanding of AGN galaxy and AGN large-scale structure connections. So this is a broad overview of many of the things that have been going on in X-ray surveys. And I won't be able to cover all of these topics today, but if you have interest in learning more about these, I do have a couple of review articles which may be of interest to you that go through many of these topics in considerable detail. Today, I am going to focus, in fact, on this topic at the bottom, the understanding of AGN galaxy and AGN large-scale structure connections. So that's where this work sort of fits into the big picture. And one basic question we are addressing is listed here, and that is we are trying to determine what properties of a galaxy drive the growth of its central supermassive black hole. There are many measurable galaxy properties that could conceivably be related to supermassive black hole growth. A galaxy's stellar mass, you might imagine, could be related. That could relate to the depth of the potential well and how well a galaxy holds on to its gas and thereby feeds a supermassive black hole. A galaxy's star formation rate could also be relevant. Star formation, again, tracks generally the amount of cold gas in a galaxy, which is also relevant to feeding of a supermassive black hole. You might also think that a galaxy's compactness, how centrally concentrated it is, has something to do with the feeding of its black hole. Or perhaps its environment, either on sub-megaparsec or, say, 1 to 10 megaparsec scales. Maybe that has something to do with, say, galaxy interactions which lead to the feeding of supermassive black holes. Or perhaps a galaxy's stellar population age has something to do with the feeding of its black hole. Those are some interesting possibilities. And to determine which properties of galaxies are truly most important for the feeding of their supermassive black holes requires large statistical samples of well-characterized AGNs and galaxies. That's because both AGNs and galaxies are complex objects. There's a fair amount of scatter, and so one needs large samples to sort of average out noise effects in the data. So as an outline for what I'm going to talk about today then, well, given the importance of data, as I've just mentioned, I'll talk a fair amount at the start about surveys data and techniques. I will then move on to talk about the key correlates of supermassive black hole growth. I'll then talk briefly about the evolution of the supermassive black hole population, and I'll end with some future opportunities. First, let's start with the survey data and techniques. So in the work I'll be describing, we utilize some of the highest quality X-ray and multi-wavelength surveys that have ever been conducted. they're listed here in this table. These are their names. These are their sky areas covered, their depths in the optical and in the X-ray, and then also the numbers of AGNs in these fields, the numbers of galaxies in these fields, and so on. And the surveys that I'll be just using today follow the standard sort of wedding cake survey design. That is the surveys we're using in this plot, which compares X-ray flux limit along this axis versus solid angle along this axis, range from ultra deep pencil beam surveys through to medium area, medium sensitivity surveys like COSMOS and SERVS, through to very wide field, shallower surveys like eFEDS. And we combine all of these surveys together to get a complete sampling of the AGN population that's responsible for most black hole growth in the universe. In our sample, we have up to 8,000 AGNs in 1.3 million galaxies. It's a stellar mass complete sample. And importantly, all of the AGNs and galaxies are well characterized, benefiting again from the fact that these fields have the best multi-wavelength data available on the sky, running all the way from the far infrared through to the X-ray band. And we utilize all those data, as I'll talk about. Furthermore, the X-ray and multi-wavelength data have been uniformly analyzed and sort of federated together in a systematic, organized way for all these surveys, so we can intercombine these surveys and not worry about cross-calibration issues. And furthermore, I want to highlight that these surveys are such that they're again the best studied multi-wavelength fields on the sky, and the data quality in these fields keeps improving. For example, we're excited in the near future about the start of operations for the Rubin Observatory. I've been involved with Rubin since about 2005, and we're excited that Rubin, of course, will be extensively targeting these fields, the ones I have listed here, and here they are shown on the sky, and that will drive even further observations of these fields and continue to improve the multi-wavelength data quality. So again, these fields are extremely well studied, and I'd like now just to take you on a little tour of some of the relevant X-ray data for these fields. The X-ray data, as we will see, is important for tracking the growth of the supermassive black holes. So first we'll talk about the sort of very narrow field pencil beam surveys. Here are two of them. These are the Chandra Deep Fields. These are the two deepest X-ray observations that have ever been made. One is in the north up by the Big Dipper, one is in the south. This one's a 2 million second exposure, this one's a 7 million second exposure over fairly small areas. And of course I want to highlight that when we make these X-ray surveys, we're not only making X-ray images, but due to the way the X-ray detectors work, we also simultaneously, while doing the imaging, also get high quality X-ray spectral data and X-ray variability data for all the sources in the fields. And to give you a sense as to how sensitive these ultra deep pencil beam surveys are, well, in the very central part of the Chandra Deep Field South, I'll show you an image of this particular region later on, the very faintest sources we're detecting are such that we have about one count coming in every 10 days. And so the data are really fantastically sensitive. Then if we move out to larger area surveys, the sort of medium area, medium sensitivity surveys, here I'm showing the XMM-SERVS X-ray surveys conducted with the XMM-Newton Observatory. And well, here, for example, you'll notice this very particular shape here. That's the outline of the Chandra Deep Field South, which I just showed you back here. And so in addition to the ultra deep pencil beam part of this survey, we now have obtained wide field X-ray coverage over about 4.6 square degrees all around that field. And we can use this ultra deep field, in fact, to calibrate our general analyses of the wide area data. We also have obtained excellent data in the XMM-LSS region, another very well-studied sky region, and in LISS-1 showed here. And for each one of these, the moon is shown, for scale. Then if we move out to even larger areas, we are now also utilizing the eROSITA eFEDS field. This is a wide field 140 square degree survey, although presently we're only using about 60 square degrees where the highest quality multi-wavelength data are available. So I want now just to say a few words about how we actually track supermassive black hole growth with the X-ray surveys. So most of the detected X-ray sources that you see in this survey and so these surveys and so on are active galactic nuclei. That is, they represent the main way by which supermassive black holes grow in the universe. And the X-rays turn out to be a very effective way of tracking black hole growth. The X-ray emission is nearly universal from luminous AGNs, so we don't have to worry about missing some significant fraction of the population. It's also, the X-ray emission is quite penetrating, especially as you go to high redshifts. And so that minimizes obscuration biases. And then finally, the X-ray emission has low dilution from host galaxy starlight. And so you don't get confusion in the X-rays between starlight and black hole related light. And then another very important point regarding the techniques that we use here is that in the work I'll be discussing today, we in fact average over samples of galaxies to track the long-term supermassive black hole growth in galaxy populations of interest. And I want to clarify that a little bit further. And so this is in fact the very central part of the Chandra Deep Field South. These are the very deepest X-ray data that have ever been obtained. And one question I ask myself when I look at these data from time to time is that, I wonder, what would this sky field look like if we had done the Chandra Deep Field South experiment, not right now, but say in 1 million years, or in 10 million years, or in 100 million years? Would it be the exact same pattern of spots up on the sky? Or rather, should the Chandra Deep Field South instead be thought of as a kind of statistical sampling of the types of galaxies that generally are growing their supermassive black holes? Well, given our understanding of AGNs and their variability, and they vary by large amounts over time, we think that this statistical nature of the Chandra Deep Field South experiment is the more appropriate way to think about these data. So one approach that we then take to beat down variability effects from inducing large amounts of noise in our analyses is we average over samples of galaxies of a given type. For example, we take a sample of galaxies of a given mass and we measure the average black hole growth in galaxies within that range of masses of interest, taking into account both the directly detected systems and then by utilizing stacking the X-ray undetected systems as well, measuring them on average, or at least placing a limit upon them. And we can thereby essentially learn about long-term black hole growth. That is, we're taking black hole growth to be ergodic so that the average over a sample of these systems is equivalent to the long time scale time average of these systems. So we're measuring black hole growth in a long-term average sense. Okay, I also want to say some words about our measurements of the galaxies. First, in our studies, we measure the properties of both the active galactic nuclei host galaxies and also the underlying galaxies in the samples that are present in these fields. Again, we want to study the black hole growth both in objects that are AGNs right now, but as well as in the objects that are not AGNs right now, because in 10 million years, those systems may become AGNs due to variability. So again, we have to average over all galaxies, not just the AGNs. The measurements that we make use, as I mentioned, the extensive multi-wavelength data reaching all the way from the far infrared to the X-rays. We have HST and JWST imaging available in some cases for morphology studies. In fact, here are some nice images showing, in this case, Hubble Deep Field observations in the, Hubble Space Telescope observations in the Chandra Deep Field South Field. These are combinations of B, V, Z, and then infrared bands. And you can see, for many of the AGNs, we can get good measurements of their host galaxy properties. And that turns out to be very valuable. Here, and this is just, of course, one set of data. Here's another set of these panels. Here's another set. And we have large numbers of AGNs. And galaxies with well-characterized properties, morphologically in this case from the Hubble Space Telescope, which we can use to learn about, again, connections between galaxy properties and black hole growth. We also utilize spectral energy distribution fitting. In this case, this is showing work from a paper where we performed uniform SED extraction and fitting for 2.8 million objects. And the X-rays help significantly in the SED fitting. They're used directly in the SED fitting to set the level of the AGN component that is present. And we're able thereby to separate these systems into galaxies versus active galaxies versus bursting and quenching galaxies and so on. And you can see the extensive multi-wavelength sampling of the spectral energy distributions, which lets us characterize these galaxies quite well. Not only can we perform improved source classification, but we can also, as I mentioned, measure galaxy properties. We can, for example, from the SED fits, get measurements of stellar masses and star formation rates. And we then calibrate our stellar masses and star formation rates by comparing them for these wider fields with ultra-deep measurements in small regions, for example, the Chandra Deep Fields South proper, where there are many more bands still. And you can see that we can do quite well in measuring stellar masses and star formation rates in these fields. Okay, so that's our measurements of black hole growth and of galaxy properties. Now I would like to talk to you about what we find in terms of the key correlates of supermassive black hole growth. I already gave you this list before of various properties that could be connected to the growth of a supermassive black hole, and we perform correlation analyses to determine which ones are truly important. As you see, there are many possible correlates of galaxy properties with supermassive black hole growth, and moreover, some possible correlates, in fact, correlate with each other. For example, it has long been known that for star-forming galaxies, the total star formation rate correlates with the stellar mass of a galaxy. That's known as the star-forming galaxy main sequence. And so one has to be able to break intercorrelate degeneracies. To do that, we perform non-parametric partial correlation analyses to determine which correlations are truly fundamental versus which ones are just being secondarily induced. And our large and well-characterized samples that I've already described help greatly in breaking correlation degeneracies. So what I'm going to do now is present some of the main results that we find for connections between galaxy properties and black hole growth, and I will suppress many complex details of the analysis, and you can see the papers that I will cite for many of the important details if you're interested. So one thing that rather immediately emerges is that for the general galaxy population, and this runs all the way from low redshifts down to 0.1 all the way up to redshifts of 4, we find that supermassive black hole growth correlates most strongly with stellar mass. You can see this here, for example. So this plot is showing the long-term average supermassive black hole accretion rate derived via that averaging process that I talked about previously versus galaxy stellar mass. And you can see there's very strong correlations across a wide range of redshifts between galaxy stellar mass and long-term average supermassive black hole accretion rate. And this spans orders of magnitude. You can see that that as you go across this range of galaxy stellar mass, the black hole accretion rate rises by, 3 or more orders of magnitude. So this is a strong dependence. Now, our analyses not only allow us to measure basic correlations like this, but we can also measure the underlying conditional probability distributions from which correlations like these emerge. This is showing effectively the effective Eddington ratio of galaxies of different stellar masses and with different redshifts. And here you see the full conditional probability distribution. That is the conditional probability distribution of the effective Eddington ratio as a function of stellar mass and redshift in the various bins. Okay, so that's That's very valuable information. In fact, these data encode a tremendous amount about how black holes grow in the universe, and we have recently performed the best measurements compared to previous valuable works of these conditional probability distributions. So one thing we find is stellar mass has a strong connection, and that holds even when you perform these partial correlation tests. Furthermore, we also have considerable interest in looking for relations that depend upon galaxy morphology. For example, we have long known now, for at least for a couple of decades, that there are clear connections between the masses of supermassive black holes in the centers of galaxies and the properties of galaxy bulges. Here's one of the famous relations here between, in this case, the luminosity of the bulge versus the black hole mass. And you can see there's a strong and fairly tight correlation there. In contrast, the correlation with, say, galaxy total stellar mass or with disk stellar mass, shown here and here, are much weaker. They have much more scatter to them, as you can see. So this indicates that morphology is likely going to be important, that the bulge and being able to measure bulge properties is going to be relevant to understanding supermassive black hole growth. So what in fact we try to do in the analyses I'll describe is we try to take effectively the time derivative of this diagram. That is, the time derivative of the black hole mass is the black hole's accretion rate. The time derivative of the galaxy's bulge luminosity or bulge mass would be the bulge star formation rate. And so we try to look at connections between black hole growth and bulge star formation rate. Okay, so how do we do that? Well, we use the morphological information coming from the Hubble Space Telescope in this case. In fact, we use 10,302 galaxies in the 5 candles fields, and we utilize machine learning morphological measurements that have been performed in the H-band to get out to the rest frame optical, even at high redshift, to separate galaxies into bulge-dominated systems and non-bulge-dominated systems. And here you can see in these top 2 panels, which are red-framed, you see bulge-dominated systems. And in these bottom 2 panels, you see not bulge-dominated systems. Now, why are we doing that? Well, the key idea here is that we are attempting to remove non-bulge components by focusing on the bulge-dominated sample so that the bulge star formation rate is effectively the total star formation rate of the galaxy. Now why is that important? Well, it's because we're not able out at high redshift to, in general, measure just the star-forming properties of galaxy bulges. And so we utilize the measurements of just bulge-dominated systems to effectively remove non-bulge components to galaxies. Why is that important? Well, it's because, as I've said, the supermassive black hole growth appears likely to be related primarily, at least, to the bulge properties rather than to the general galaxy properties. Okay, and indeed, then, when we look at bulge-dominated systems in the distant universe at redshifts of 0.5 to 1.5 and 1.5 to 3, we find that there is a notable correlation between this long-term average black hole growth that we measure from the X-ray data with the star formation rate, which again is effectively the bulge star formation rate for bulge-dominated systems. For comparison, if you look at non-bulge dominated systems, there may be a bit of a correlation there, but it's much weaker, likely because there are non-bulge components present in these systems that are messing up your measurements of star formation rate. Note that our results span a wide range of redshift and reach out to the peak era of supermassive black hole growth. And of course, not only can we note there's a correlation there, but we can fit the correlation. This is our best fit. You get the same consistent fit in both redshift bins as best we can measure. And the fit is such that for the bulge-dominated galaxies is such that the ratio of black hole accretion rate to star formation rate is about 1 part in 302, which is similar to the typical black hole mass to bulge mass measured locally. So we actually can see that if you allow this growth to occur over a long span of cosmic time, you might naturally produce the local relations between black hole growth and star and bulge properties, black hole mass and bulge properties. We take this to be evidence of true coevolution, since we observe this apparent lockstep growth of supermassive black holes in their bulges, at least over this redshift range. And I will also mention that subsequently people have made useful measures using, for example, reverberation mapping as part of the Sloan Digital Sky Survey reverberation mapping project, have measured black hole masses now out into the distant universe, sometimes fairly reliably. And as you would expect from these results, where you don't find redshift dependent changes in the ratio of black hole growth to bulge growth, you find similarly that we don't find much evidence for evolution in the black hole mass relative to the bulge mass as you go out to high redshift. Okay, so that's very nice. This result and these results are nicely consistent with each other and sort of reinforce each other. So that's another interesting connection. And then another one we find is that the AGN host galaxy compactness also appears to play a role in black hole growth. Compactness is a measure of the kind of mass surface density of galaxies. Here's one way it's commonly measured. You measure the stellar mass within 1 kiloparsec and average that out over 1 kiloparsec area. And at least for gas-rich star-forming galaxies, this sigma 1 parameter may also serve as a tracer of central gas density on a kiloparsec scale. We measure this sigma 1 parameter using in the rest frame optical using Hubble Space Telescope data, in this case from Cosmos and Candles. Qingling Ni did those measurements. And if you then want a sort of a visual understanding of what this compactness means, well, here you can see that for galaxies that all have about the same stellar mass, you can see that as compactness runs from low values over here through to progressively higher values as you move rightward, the galaxies morphologically become apparently more compact. Okay, so what do we find here in terms of connections between black hole accretion rate and compactness? Well, the black hole accretion rate, long-term average again, versus compactness is shown in this diagram specifically for star-forming galaxies. And notably, you see there's a quite clear connection, again spanning a couple of orders of magnitude in black hole accretion rate between, again, galaxy compactness and black hole accretion rate. And this correlation, if you look at it at sort of low redshifts in black to sort of higher redshifts in blue to the highest redshifts we can measure in red, appears to systematically shift upward as you go to high redshift. So there is a clear correlation there, but the correlation appears to evolve with redshift. And I will note that while we see these results for star-forming galaxies, we do not see similarly strong correlations for quiescent galaxies. That suggests that gas density indeed may be playing a role here, as I had mentioned back here, that for gas-rich star-forming galaxies, we may be tracing central gas density, which is relevant to feeding the black hole. Similarly, the redshift dependence that I've shown here can also be understood via gas evolution. Galaxies at high redshift are more gas-rich, so that could explain that as you go toward lower redshift and gas thins out, the connection drops in its normalization. Furthermore, this connection between compactness has the prospect for explaining other interesting systems. For example, if you look at, again, these connections between black hole mass and bulge properties, there are some outliers, such as this one shown here, which appear to lie well above the overall trend. This galaxy is actually a rather compact galaxy, and in fact, Qingling Ni has noted that some of these outliers, which are often referred to as supermassive black hole monsters, because the black hole is so much more massive than you might expect at that bulge luminosity or bulge mass, that these black hole monsters may be lying above due to compactness effects playing an additional role in the generation of the black hole. Okay, and then finally, I want to say a few words about cosmic environment. And you may know that there have been some notable results in recent years, I've been involved in some of them, whereby X-ray observations of high redshift clusters and protoclusters often are finding luminous obscured systems or fast supermassive black hole growth in high redshift protoclusters, suggesting that at least at high redshift, there may be some notable connection between a galaxy's overall environment and the growth of its supermassive black hole. We've tried to address this more systematically to the extent that we presently can, utilizing the Cosmos data. Cosmos by far still has the best measurements of cosmic structure of any of the fields that we've analyzed. And in fact, a man named Darvish has performed very useful measurements of structure in the Cosmos field, particularly in the ultra-vista part of the Cosmos field, which gives you the very best possible measurements. Measurements are performed both at sort of 0.1 to 1 megaparsec scales, shown here using this overdensity parameter, and then here on sort of 1 to 10 megaparsec scales using a multi-scale morphology filter algorithm, which separates the environment into field environment, filament environment, and cluster environment. And this is done as a function of redshift. Darvish has derived about 310 redshift slices spanning this wide redshift range based upon something like 170,000 galaxies, which contain about 2019 X-ray AGNs. And we have this, and these measurements in the Cosmos field allow us to probe environments, as you can see, ranging from the field up to sort of low mass clusters with halo masses of about 10 to the 14 solar masses or so. And that range of cosmic structures actually contains most of the galaxies in the universe. So then we've looked for dependencies of black hole growth upon cosmic environment, and surprisingly, we don't really find much, and you can see that here. These are plots, again, on sort of 0.1 to 1 megaparsec scales and 1 to 10 megaparsec scales in different ranges of redshift, as shown from the top panel to the middle panel to the bottom panel. And you can see that there is a clear dependence of black hole accretion rate upon stellar mass, which I showed you earlier. But then if you split your samples into different environment groups, for example, looking at overdense regions shown in red and lower density regions shown in blue, they don't really separate out very much, indicating that there is not much of an environmental dependence. That is also found on larger physical scales, where here we separate systems into field, filament, and cluster systems, and you can see there's not much separation as a function of environment. So our sort of partial correlation analyses, and here is a plot that actually shows the detailed partial correlation analyses, indicate that, for example, stellar mass resoundingly beats overdensity in terms of what drives supermassive black hole growth. And again, you can see that graphically here, that environment really doesn't seem to matter all that much, and that at least for the range of mass structures that we can probe, again up to about 10 to the 14 or so solar masses, we don't find a significant dependence upon environment for black hole growth. Now that contrasts a bit with these studies, which I've already highlighted, but these of course are homing in on the very rare, most massive structures in the distant universe. So perhaps as one goes up to even higher mass structures, there does arise a dependence of black hole growth upon environment, and it will be very valuable ultimately to connect studies like these with studies like these, and we're working on such studies at present. Okay, so those are some of the results that we found. Now I would like to talk about this work that I had mentioned on the evolution of the supermassive black hole population. This work is presented in this recently published paper led by Fan Zhao, an excellent Penn State graduate student. And in this work, as you can see from the title, we perform a sort of hybrid synthesis of black hole growth using observations of black hole growth by accretion and simulations of black hole growth by mergers. So as you no doubt have heard, there are two main mechanisms by which black holes can grow. Accretion of gas, shown over here on the left, and then mergers of supermassive black hole, which redistribute mass within the black hole population here on the right. And we have already done extensive studies of growth by accretion, but there's always been this remaining issue of mergers and how much of a role they can play. And we have now been working to tackle that, and this is how we do it. So we utilize a hybrid approach. We utilize observations, which constrain the accretion channel quite well, but presently do not very effectively constrain the merger channel. And we also utilize simulations, which provide us with a reasonable estimate of the merger channel for black hole growth, but presently give an unreliable assessment of the accretion channel. And I'll say more about that in a minute. And thus, a hybrid approach where we utilize the observations of the accretion, where that's good, and then simulations of the mergers is promising. And that's what we do, and here's how we do it. So we utilize, again, this strong dependence that I previously showed you of black hole accretion rate upon galaxy stellar mass, and we combine that with numerical simulations, specifically with illustrious TNG, which is one of the best simulations of galaxy growth in the universe. And the folks who work with illustrious TNG argue that their simulation can effectively reproduce many properties of the galaxy population, including the stellar mass function, the star formation properties of galaxies, the gas properties of galaxies, the sizes of galaxies, the colors of galaxies, and so on. And so we take their measurements of galaxy growth and we combine them with what we believe is a better assessment than what they use. I'll say more about that in a minute, of black hole growth. So that's how we're playing the game. And again, these measurements let us track the accretion, and illustrious TNG allows us to track the mergers of black holes. Okay, now, again, as I just mentioned, you probably know that the illustrious TNG folks, of course, also attempt to include black hole growth in their simulations. And in fact, this is quite important because black holes provide feedback out into the galaxies. And so if you want to capture black hole growth, you need some parameter. You want to capture galaxy growth, you need some inclusion of supermassive black hole growth, and especially supermassive black hole feedback, which can affect galaxy properties. So the issue that we find is that the subgrid accretion physics that is present in illustrious TNG for treating black hole growth likely needs improvement. Why do we say that? Well, that's shown in this plot here. In this plot, we show the accretion rate onto black holes derived from our observations as the dashed lines at redshifts of 0, 1, 2, 3, and 4. And then we show what the illustrious TNG simulations say the accretion is doing. And you can see there are wide discrepancies between the observations and the simulations. And the discrepancies are complex. In some places, the simulations are above the observations. In other places, the simulations are below the observations. But there are very clear differences going up to order of magnitude or more level discrepancies. I would say this isn't that surprising because when the illustrious TNG folks attempt to treat the black hole accretion, they're forced to do it with a subgrid approach that is quite simple. They utilize basically Bondi-Hoyle accretion to measure the accretion rate to estimate the black hole accretion rate, and they add an Eddington limit on that. And then they also include either kinetic or thermal feedback, depending on how fast the black hole is growing. And they've done their honest best to track black hole growth, but unfortunately, at least the present simulations don't seem to agree very well with our measurements of what the black hole growth is actually doing. This point has been noted by other authors before. Habazit et al. Have noted the same points in earlier work. So what do we then do in this sort of tracking of black hole growth? How do we actually practically do it? Well, we basically iteratively solve this little equation that I'm showing here repeatedly. This equation basically tracks the growth of a black hole as it goes downward in redshift, and we take the black hole's mass to be what it was at a higher redshift, plus the growth due to accretion, which we get from observations as a function of galaxy stellar mass and redshift. and then growth due to mergers. I'll say more about this one in a minute, but this one's coming from the simulations. We start solving this little equation at a redshift of 4, and we find, as is usual in this kind of work, your sensitivity to the initial conditions that you seed the black holes with fades rapidly, at least for high galaxy stellar masses. Now, we do our best with the initial seeding. We use the black hole mass, galaxy mass relation of Rains involuntary to seed these systems at a redshift of 4. But again, the dependence upon the initial conditions is generally very weak, and that happens rather quickly due to all the accretion growth outstripping the initial seeded masses. The time step available to us from TNG is about 0.15 gigayears. And remember, in this work, we track the mean growth by accretion, averaging out, because remember, we perform these average measurements. So we average out accretion-based fluctuations. So we're tracking things in the mean, not trying to capture the underlying scatter due to accretion variations. And then regarding the mergers, well, there, of course, every time a pair of galaxies merges within the TNG simulations, there is at least a prospect that the two black holes present will also merge. Now, that's not guaranteed. The two black holes may wander around for a very long span of time. And we utilize merger probabilities for the black holes from a paper by Tremmel et al. In 2018. And we also set upper limits by setting p merge to 1. That is, every time a pair of galaxies merge, we allow the black holes also to merge. And this plot here, first of all, shows our sort of comparison of the overall importance of black hole accretion versus mergers to supermassive black hole growth in the universe. And the bottom line is that, as you can see, the accretion dominates. At high redshifts, it dominates by a wide margin. And then as you go to lower redshifts, the accretion drops off, and their mergers may become fractionally significantly more important. In fact, down here shows the fraction. The mergers are shown both with our sort of expected level of mergers, utilizing this merger probability from Tremmel et al. And then we also show a sort of maximum merger rate, which again comes from allowing every time you have a pair of galaxies merge, allowing their black holes also to merge. And even in that case, you can see it's only at the very lowest redshifts do mergers actually ever come to dominate. And for the expected case, mergers never dominate. Now, because we're simulating everything, we can also work this out as a function of galaxy stellar mass. And so here you're seeing, going down in redshift, the growth rate from both accretion and from mergers as a function of galaxy stellar mass. And you can see that, well, the place where mergers are fractionally most important are up at the highest stellar masses, up at sort of 10 to the 11 solar masses and more galaxies, is where mergers may actually be competitive with accretion, starting at around a redshift perhaps of 1, although even there they're probably below. But at a redshift of half or so, you could actually get, as you can see, for large stellar masses, you can have the mergers being entirely competitive with growth by accretion there. And that's because the accretion growth is just dropping off so rapidly. So we now have good quantification of where mergers might actually dominate, and this is relevant for future predictions of what gravitational wave experiments might find. We also can track the buildup of the overall supermassive black hole mass function, again, including both accretion and mergers. So here is our seeding of the black hole mass function at a redshift of 4. And then you can see by a redshift of 3, there's already been a lot of growth, leading to the sensitivity to seeding dropping off rapidly. And then as you go to redshift 2, the growth continues. It continues down to a redshift of about 1. And then the growth largely freezes out. And you can see that here from the fact that the blue and purple curves are rather close to one another. And that's due to the accretion dropping off so much that further growth is much smaller than the growth that happened earlier, as you would expect. This plot here answers the question of where is the mass. And you can see this is the probability distribution from the 5 to 95% percentiles, and then the 25 to 75 percentiles, and then here's the median. And as is separately known, at low redshift, your typical black hole mass, where most of the mass is somewhat above 10 to the 8, and that drops some as you go to higher redshifts. We're quite excited in the future at comparing our predicted black hole mass distributions quantitatively with good quality measurements of black hole masses. And now, of course, there are large numbers of black hole masses being generated quite reliably from reverberation mapping. This is a nice plot showing, perhaps the key result from the Sloan Digital Sky Survey Reverberation Mapping Project. And this combines data from Yue Shen and Kate Greer and Yazaman Hamayani showing black hole masses over a wide span of cosmic time, spanning about 85% of cosmic time, in fact. And these should be quite good masses coming from reverberation mapping. And so if we can unwind the underlying selection function from which these black holes were targeted, we can then make comparisons with our predictions. And we look forward to doing that in the future. We can also look at the relation between black hole mass and galaxy stellar mass. And we find that the recovered black hole mass stellar mass relation is in fact lower than the ones that are measured dynamically in the local universe. And you can see that here. Here are measurements in the local universe, and here is what our simulations predict. In fact, our simulations agree better with the black hole mass stellar mass relations found for broad line AGNs, and furthermore, they agree better with the so-called debiased relation between black hole mass and stellar mass that Shankar et al. Have put forward, where they have argued that there are selection biases that go into the measured local relations measured straight up, and if you don't correct for those, your results are biased, and they suggest the real relation is down there, which notably agrees better with our simulation. So that suggests that perhaps Shankar et al. Are on the right track, which is very interesting. We also find, as you can see, that the black hole mass stellar mass relation also does not evolve much over the redshift range from 0 to 3. And that's consistent with other constraints. You can see that here in this lower panel. Again, these are measurements from the Sloan Digital Sky Survey Reverberation Mapping Project. And in this lower panel, the black hole mass is shown as a function of total galaxy host mass, and that also doesn't seem to evolve much with redshift, rather consistent with what we find from our simulations. We can also notably calculate the scatter of the black hole masses at a given stellar mass, and we find that scatter can in fact explain much of the observed scatter. And so you can make comparisons not only of the sort of average value, but you can compare the amount of scatter, and we can predict that fairly well too. Okay, finally, our results let us also address a number of other interesting topics. They let us, for example, place our galaxy's supermassive black hole in context. It's well known, of course, that our galaxy has a 4.3 million solar mass black hole in its center. Here is our galaxy shown here in terms of its stellar mass and its black hole mass. And notably, if we compare our galaxy's supermassive black hole and with the black holes in galaxies that achieve the same stellar mass that our galaxy achieves, we find that our galaxy's black hole mass is notably low. In fact, it's notably low by about a factor of 7. It's about 7 times undermassive compared to the median black hole mass for other galaxies with similar stellar masses. And you can see that here. Here is our median growth track for galaxies that end up with the Milky Way's stellar mass. They generally produce more massive black holes than our galaxy seems to have produced. Now, why is that? Why is our galaxy producing a black hole that's so undermassive? Why is our galaxy underperformed? Well, there's several possibilities there. The most straightforward way to explain that would be that perhaps our galaxy, compared to other galaxies that end up at the same stellar mass, actually grew at somewhat lower redshift. And the reason that's relevant is growth at lower redshift gives you sort of less bang for your buck, as you can see from this plot, in terms of black hole growth at a given stellar mass. So as a galaxy grows upward in stellar mass, if it grew later in cosmic time, it doesn't grow along these tracks, it grows along these tracks where you get less mass. So perhaps that's an indication that our galaxy may have grown relatively late compared to other galaxies with matched masses at redshift 0. Now, that being said, this undermassive nature of our galaxy's supermassive black hole is interesting, but our galaxy is actually not that strong of an outlier due to the fairly large scatter in black hole mass. That is, if you look at the range of black hole masses, this is the median value. There's a wide scatter around it. And I believe it's like such that our galaxy is just shy of being a 2 sigma outlier. So it's not that extreme, but it's interesting. And one possibility, as I've already said, is perhaps our galaxy grew late. But another possibility is that, again, there may be other sources of other correlates of black hole growth that are relevant that are not being captured by our present simulations, and that's something that's interesting to explore in the future. Okay, I will end today by talking about some future opportunities for advancing this work. One thing that we're excited to do, of course, is just to continue improving these well-studied survey fields. We already have superb data in these fields, but the data are going to continue to get better and better. I've already talked about how the Sloan Digital Sky Survey is measuring direct black hole masses in these fields. That's exciting. Also, there are numerous powerful spectroscopic surveys, either completed or just coming online, that are being conducted in these same survey fields that will give us huge numbers of spectroscopic redshifts. That will be very valuable for improving our analyses. Also, as I've mentioned, the Rubin Observatory will extensively target these fields as its deep drilling fields. So we're very excited about the Rubin data and using that to study the variability of these systems, using it to just get better measurements of galaxy properties. We're also excited, of course, about the Euclid data, ultimately Roman data, data from Toltec on the LMT, and so on. So there's tremendous amounts of data coming in these well-studied survey fields. Now, in addition to just the well-studied survey fields, of course, there are many wide field facilities coming online. Again, Rubin, Euclid, Roman, Xuntian, they will all conduct, in addition to sort of their deep drilling field type surveys, will also conduct very wide field surveys, as will ASCAP in the radio, as well as will wide field spectrographs. And one can hope to combine measurements from all these wide field surveys with the enormous numbers of X-ray observations that have already been gathered over the past 25 years now with Chandra and XMM and NuSTAR and now eROSITA. And we can build up truly massive samples which have quite high quality multi-wavelength data coming from these very wide field surveys and get even better samples to study all of these phenomena. And then furthermore, we look forward to improving this sort of observation plus simulation-based tracking of black hole growth. In fact, I think utilizing improved simulations where TNG or other simulations actually utilize better measurements of black hole growth when they perform their simulations, I think will be very valuable. And as I mentioned, one could also aim to enlarge our predictor set, where right now we're just using stellar mass and redshift. You could also hope to bring in bulge properties, compactness, and so on to track black hole growth better there. And then finally, we of course are very excited about next generation X-ray surveys with New Athena, which is now scheduled for launch in 2037, and with the AXIS probe, which is currently being developed under review at NASA. And these facilities will allow us to get much better wide field surveys with very high sensitivity, reaching around the sensitivity or even beyond the sensitivity of the Chandra Deep Fields, but over much larger sky areas, giving us much larger samples. That will be extremely valuable. And these facilities will also, of course, provide much improved X-ray spectral characterization of the detected AGNs, which is also very valuable. So with that, I will stop and thank you.